Hello, my name is Ramon Lopez, professor of physics at the University of Texas at Arlington, and I'm going to talk a bit about sunspots. So the story really does, of course, begin with the sun, and occasionally you see these spots. You see this little one floating across the surface there, but then later in this month of August in 2006, you see a big group of sunspots there on the face of the sun. And the earliest reference to sunspots is actually in the I Ching, which is the book of divination of the Western Zhou dynasty. And it was compiled in the 9th century. And certainly by the 3rd and 4th century, it was being widely used in pretty much its current form. And really by 28 BCE, sunspots were regularly being recorded in imperial Chinese annals, because the Chinese astrologers would record everything in the sky because they had to use it for divination, and things that occurred in the sky that were not explainable or that might have been connected to some occurrence could, and the emperor wasn't happy with whatever had occurred, could end in execution of the court astrologers. So they were very diligent about recording all kinds of things. They were first mentioned in the West by Theophrastus in the 4th century BCE. Theophrastus was a close friend of Aristotle. He was a student of Plato. He succeeded Aristotle in the school in Athens when Aristotle had to leave after the death of Alexander the Great, and anti-Macedonian feelings were rising in Athens. And Theophrastus made all kinds of observations, especially around plants, and he's known as the father of botany, but he mentions sunspots in his treatise about weather, and tries to connect the appearance of sunspots to rain. They weren't very much mentioned in the West after that, and in fact, in medieval Catholic Church doctrine, the sun was supposed to be a perfect sphere, and so they just, the issue of spots on the sun, some stain on the perfect sphere, did not really come up. But in 1610, 1611, there were telescope observations made by various Europeans, including Galileo, who argued with other people about who saw them first, right? But it was Galileo, because Galileo was so famous. It was Galileo who made them famous in Europe by writing about them, even though, they had been observed and talked about for over 2,000 years before then. But that really marked the beginning of sort of a scientific examination of sunspots. And in the mid-19th century, Heinrich Schwabe reported that the number of sunspots varied with a rough period of about 11 years. And that was the sunspot cycle. So this is the beginning of really understanding what are the periodicities, what are the patterns that emerge from sunspots. And to get that pattern, you need to count them. So exactly what is the sunspot number? It's not exactly the number of spots. Rudolf Wolf created a measure of sunspots where he said, well, let's take the number of groups of sunspots and multiply by 10, plus the number of individual spots. And then depending on the observer and the conditions, et cetera, we'll multiply all of that by some kind of observational normalizing factor. So that Wolf number was calculated for many years. And here you see the average sunspot numbers. Now, actually, the Wolf number in these early years are not really that kind of observation. They're reconstructions from various data sets. But one thing that is real is this gap of some 50, 60 years in any discernible sunspot activity on the sun. And that is known as the Maunder minimum. And we know that it's real because people at the time wrote things like, Galileo wrote about these sunspots, and I've been looking at the sun, projecting the image of the sun through a telescope, and I don't see any. And what is this? So you've got people who are writing things like that during that period. And auroral activity was very, very low during that period. So, and then there are other proxies that indicate that solar magnetic activity was at an extremely low level during that period. And then we have other reductions in sunspot activity, like in the early 19th century, the Dalton minimum. And throughout the 20th century, we've had actually a fairly large number of sunspots, the modern grand maximum. Now this graph only goes to 2000, but the number of sunspots in the peak of the sunspot cycle has been going down. Again, the study of sunspots discovered all kinds of patterns. And here in this graph generated by David Hathaway at NASA, you see what's called the butterfly diagram that was first produced by Maunder. Sunspots start at higher latitudes, and then they drift towards the equator, where they seem to sort of cancel each other out or vanish. And then a new sunspot cycle starts up again, and they appear at the high latitudes again. And actually what's happening during the whole sunspot cycle, the solar cycle of 11 years, is that the main dipole moment of the sun is reversing direction. So to go all the way around 360 degrees, it's actually a 22-year cycle. Now what's plotted down below is not actually the sunspot number, but the amount of area that is covered by sunspots. And you can see, the 20th century grand maximum, and this actually now goes out to the last couple of solar cycles, 23, 24, and you can see that the amount of area covered by sunspots is less, and in fact, the number of sunspots has been rather low as well. Now, even though the area might be large, and by large, I mean a fraction of a percent, surprisingly, the total solar radiance goes up when there are more sunspots, even though the spots themselves appear dark. The surrounding area actually is a little bit brighter, and that overcomes the loss of light from the dark region. And so total solar radiance actually is correlated with the sunspot cycle. It's not a huge variation, but it's there, and it's enough to drive interesting phenomenon. And so what causes sunspots? I mean, what is happening? And really, sunspots are a magnetic phenomenon. It's happening underneath the surface. So the sun rotates with differential rotation, which is to say that at the equator, the sun rotates faster than at the poles. And so as the sun rotates faster at the equator, I mean, the magnetic field is dragged with that rotating material, because the sun is composed of plasma, electrically conducting gas. The electrons have been stripped from the atoms. And so because it's electrically conducting with essentially infinite conductivity, the plasma and the magnetic field are stuck together. And so as the plasma moves, the magnetic field has got to be dragged with it. And so that wraps up the magnetic field. And now there's energy in that magnetic field. There's energy in that twisted magnetic field in particular. And that energy is being taken out of the motion of the plasma and put into the magnetic field. And eventually it'll have to be released. But after many, many rotations, you get a lot of twisted magnetic field on the sun. And the twisted magnetic field can form bundles of magnetic field flux tubes. And because the magnetic field has got an energy density, a pressure, it pushes plasma out. Plasmas are naturally diamagnetic. They're pushed out by a magnetic field. So while you might have a constant pressure across some region just inside the surface, the photosphere of the sun, there'll be different densities, because if you've got a region of high magnetic field, you'll have lower plasma pressure. because the sum of the plasma pressure and the magnetic pressure will be constant for pressure balance. But because the tube has got concentrated magnetic field, it pushes plasma out, and so then it's lighter and it will float up. And now what will try to hold the tube down is that bend, again, that twist, bending the tube up requires force and stores energy in that magnetic configuration. But it can happen, and the tube will rise up to the surface and pop through, and then you get a sunspot. And sunspots are always in pairs. There's always a north and a south because it's connected to this tube, and the magnetic flux in that tube is conserved along the tube. So that's physically what a sunspot is. And in the center, the magnetic field comes straight out, and on the edges, it's more inclined, more horizontal. And then this forms loops in the solar atmosphere of magnetic field. And so why are they dark? That umbra, the center dark region, that's the region of vertical magnetic field. It's the strongest magnetic field. The temperature is a bit lower there because the plasma has been pushed out by the magnetic field. So, so it's a bit cooler. I mean, it's still hot, but it's a bit cooler in comparison to the neighboring regions. The penumbra, it's a little bit hotter than the umbra, and so it's brighter, and you see these sort of streaks, those lines. That's because now the magnetic field is more inclined and has got more of a horizontal component. But that's why, you know, a sunspot looks dark. It's just in comparison to the much brighter area around you. You can see similar things actually if you take a small light bulb, like a flashlight light bulb, and hook it up to a battery, and you get a dim light of that out of that. You can see it, but then if you hold that light bulb up next to a very bright light bulb, say 100-watt light bulb in a lamp, the little light bulb will appear dark in comparison to the bright light bulb. And it's the same sort of thing with the sunspot. Now, as I said, all of this magnetic energy is stored in the magnetic field, and it erupts through the surface in the form of these spots. And you've got all this twisted magnetic field in the sun, and the sun is continually twisting up magnetic field. So how does it untwist if the plasma and the field are fixed together? Well, there's a process, a fundamental process called magnetic reconnection, illustrated here from a diagram from NASA's magnetospheric multi-scale mission, which is a 4 spacecraft mission that's studying the process of reconnection. And reconnection happens on a very, very small scale because it involves fundamentally the electrons, which have got very small radius of gyration around the magnetic field and very high frequency. So small time scales and or high frequency and small spatial scales. And there are processes that allow the magnetic field and the plasma to decouple in this very small region where the electron physics is dominating the situation, and create what's called a magnetic reconnection region. And that allows the magnetic field essentially to slip past the plasma, for the plasma to let go of the magnetic field, and for that stored energy in the magnetic field to be released and released as kinetic energy back into the plasma. And this is what has to happen to, let the magnetic field relax to a lower energy configuration. And so that's happening over the course of the solar cycle, and it happens in these various storms and magnetic eruptions. And we see here from the NASA's TRACE satellite an eruption, and you see the energy going into the plasma gets heated up, and then you can see it tracing out these magnetic loops. But actually before then, the magnetic field was even more twisted and configured with stored energy. And here from the Solar Dynamics Observatory, we see another example, in this case, a release of a cloud of plasma, because reconnection has cut the ties of this cloud of plasma and magnetic field that now goes out into the solar system as a coronal mass ejection. And those clouds of magnetic field are taking that twisted field with it. So the sun, over the course of the solar cycle, gets rid of all that twisted field by reconnecting it, releasing the energy, and also throwing that twisted field out into space in these huge magnetic clouds. And that's how it uncoils itself. One solar physicist likened it to a snake shedding its skin. So in summary, sunspots are the visible indicator of solar magnetic activity, and they occur because of the differential rotation of the sun, creates magnetic flux tubes, rises to the surface. Now, why this happens on this 11-year time scale, it seems to happen on a very similar time scale for the sun-like stars. We don't really know. There's a lot about it that we don't know. There are a few things that we do know. There's a lot of stuff we know we don't know, and who knows what we don't know yet about sunspots and solar magnetic field. But that twisted magnetic field that the sunspots are the indicator of is released from the sun in the form of eruptions, including coronal mass ejections. And that's why there's an 11-year cycle to solar activity and magnetic storms. And the solar cycle then is that periodic variation of sunspots with roughly an 11-year cycle, although there can be big variations such as the Maunder minimum, the Sporer minimum, and looking at other sun-like stars, and we can get a rough idea of their solar cycles by estimating the strength of the magnetic field in the photosphere, which you can do actually from spectra. You can look at spectra and look at something called Zeeman splitting, and that's a splitting of magnetic lines due to magnetic moment interaction with the magnetic field, and the amount of the split, the size of the split in the wavelength, is directly proportional to the magnetic field. So you can use that to measure distant magnetic fields of stars, and we see the magnetic fields of sun-like stars rising and falling, anywhere from 7 to 14 years. So 11 years is right sort of in the middle of that, and we also see that sometimes in these sun-like stars of similar mass and luminosity to the sun, that their magnetic activity cycle will turn off, or maybe it was off and it turns back on. So other stars like our sun seem to have things like a Maunder minimum phases as well. So, and how and why that exactly happens, we still don't understand. But if you're talking about period and amplitude and frequency, and trying to communicate those ideas to students, having them look at the variation of sunspots over those cycles is a really good way to do it. And you can also make predictions, like when do you think the next solar maximum will be? And nobody knows. That's the great thing. People can make predictions, students can make predictions, and then the quality of the prediction is judged on what's the reasoning behind that prediction. And then you just wait 11 years and find out. All right, thank you very much.